for me be able to be here and talk about our little work. This is a joint work with my advisor Juan Monterde. So this is the structure of my talk. I will start with a motivation and background about why we are interested in this kind of surfaces. Then an important subfamily of these constant Jordan angles surfaces, and then the method that we use to build this family, and another kind of families that we have built with our method. And in the last section, the most important result that we have for now that I want to explain. So let's get started with the motivation and background. Our line of work of mine and my advisor can be defined as we are trying to characterize different geometrical properties through the local scalar invariants. I am talking about the Gauss curvature, the norm of the mean vector, and so on. Later I will list all of them. And in a previous paper, we have characterized when a surface in R4 is contained in a sphere in terms of its invariant. And this result was in some way, it was parallel to the classical result that says when a curve, a spatial curve, is contained in a sphere in R3. So now what we aim to obtain is to characterize when a surface has constant Jordan angles, that is a kind of extension of the helix curves. So the classic result is the Landgraf theorem, and let me recall it, that it says that a curve is an helix, and an helix is that its tangent vector makes a constant angle with a fixed line, and the result is that this happens if and only if is curvature and torsion, this ratio is constant. So we are trying to obtain this kind of result when we have constant Jordan angle surfaces in terms and a condition among their invariants. So as I said, the constant Jordan angles is like a generalization for an helix surface, and roughly speaking, we say that a surface has constant Jordan angles if the tangent planes have the same angle with a fixed plane. We have a fixed plane, we compute all the tangent planes and compute the angle between all the possible tangent plane and the fixed plane, and it has to remain the same. So this property has been studied before, and in R4 the most important paper that we have found is by Pierre Bayard and Antonio Di Scala, Osvaldo Sunacastro, and Gabriel Ruiz Hernández, the name surfaces in R4 with constant principal angle with respect to plane. Here they show an existent theorem for any pair of angles. There is a surface that has these angles as a constant Jordan angles, and they show explicit example, but they are only shown for the angles 0 and half pi, which is the Clifford torus, and 0 and another angle, and this construction is made with a product of an helix of this constant angle with an straight line. So the main goal, at least at the beginning, for this talk is to show how we were able to build explicit example for any pair. Not only that exists, but we have examples, and the angles that we are going to consider is different from 0, different from themselves, and different from half pi. So what are the Jordan angles that I am talking about? we have a definition by inheriting that is for any subspaces in any space, but we are only interested in that for subspaces in dimension 2 and in R4. So the definition is you have two planes, capital pi and capital rho, and two orthonormal bases for each subspace. These are subspaces. So you consider the matrix of all possibility scalar products, and then the Jordan eigens will be the values such its cosine is the singular values of this matrix. Another way to compute that maybe is more graphical or more direct. Sorry. Is you compute the determinant of this matrix and the Frobenius norm of this matrix, and then you can compute easily these values with these formulas. And what we are looking is a surface that you make this computation from a fixed plane, R1 and R2 are fixed, but pi1 and pi2 are the orthonormal basis for the tangent plane, and we want that the values do not depend on the choice of the point. This is the formal definition, that is just what I have said. You have an immersed surface in R4, a fixed subspace, then we say that it is an elliptic surface, or we say that has constant principal angles. If the principal angles between the tangent planes and this fixed plane do not depend on the choice of the point. And we also say we like to call these surfaces constant Jordan angle surface that has constant Jordan angles, and we call it constant Jordan angle surface, or we also say a helix surface. So why we can't use the existent result, the proof of the existent result found in the paper? Because they start with amount parameterization of the surface. So the condition of having constant Jordan angles, they found that it's equivalent to have a partial differential equation system. This system is equivalent to a second order PD. And they directly use the Cauchy-Kovalevsky theorem that assures the existence of solution, but it's not possible to obtain explicit solutions with this theorem. So, before I start with how we build different examples, there is a family of subfamily of constant Jordan angle surfaces that it is interesting for our goal. So this family can be explained without our method. This is what I'm going to try here. First, I would like to say that we are going to fix capital pi as the subspace generated by the first canonical vectors. And we are going to suppose that we have an arbitrary pair of angles, which they will be phi1 and phi2. And now, as I said, we have methods, and this family is also the most simple family that we have found. And it can be explained with a kind of product between two planar curves. The planar curves that we are going to make a kind of product will be logarithmic spirals that makes some sense that they appear because they have the property that any radial line has the same angle when cross the curve. It's always the same angle. So there is some geometrical idea behind this. A Cartesian product of two curves of this style could be parameterized in this way, but a Cartesian product of plane curves is always a constant Jordan angle surface of angles 0 and half pi. So instead of using directly the Cartesian product, let me write this expression, which for one hand is like the Cartesian product because we have u, the first variable, in the first coordinates and the second variable in the second coordinates, but we have mixed in some way the coordinates with the exponential part. So all the constants are positive, and we call this family T because the limiting case of A equals 0 and B equals 0 is the Clifford torus. So the T is because we call this family T. And it is, you can compute it, and it has constant Jordan angles with the plane pi. And these are the values of the angles. And this is because, and this is a very easy way to explain this family, so we take advantage of that and I can explain. So why this is an interesting family for me and my advisor? Because they verified a kind of Lancret property. I mean, let me list now the invariants we are working with are the little invariants. There are the square norm of the curvature vector, the generalized Gauss curvature in surface for R4, the normal curvature, and the resultant. So these are the local invariants we study for this family, and what we get, this what the family, is that the Gauss curvature and the normal curvature is vanishing, and it was known that happens always for a constant Jordan angle surface. But we also found that this family has that the ratio between the fourth power of the square of the mean of the norm of the mean vector over the resultant is constant, a constant which depends on the angles. And this property we found that it is exclusive for this family inside the big family of constant Jordan angle surface. So before I can show why it is an exclusive property, I have to explain our method and the examples. So what we change about the approach in this article? Well, we start with this proposition that says that an helix surface, a surface is an helix surface if and only if its Gauss map belongs to a product of cycles. So this is made studying the bivectors associated with the tangent planes, which is very natural because you can study the tangent planes through bivectors and you have some things easier. And as I said, we have a fixed plane and fixed angles, given angles. So let me recall, in order to explain the result, let me recall the bivector notation. We have the space of bivectors, and we consider the identification about the subspaces with the set of the bivectors which are unitary and decomposable. This condition is called decomposable, and this means that from the bivectors you can get back two vectors that define this bivector. So you have this identification. Let me also recall the Hodge operator, which is defined by this expression. And the important thing about this operator is that it splits Q, this subset, into two subspaces that are the invariant for the Hodge operator and the bivectors who change the sign with this operator. So each one of these subspaces is isomorphic to an sphere. So you can take an adapted basis for this operator. That means that the first three are as subbasis for the subspace E plus, and the last three are as basis for E minus. And for our situation, let me write clear that nu1 and nu1 bar are exactly the bivector which is the sum of the bivector associated with capital pi with the bivector associated with the orthogonal of capital pi and the subtraction. So how do you use these bivectors to study the Jordan angles? This is made because if you have two bivectors, you can define two angles like you will do with vectors in R4 with a scalar product, and we define one angle which is the product with the basis for the first plane or subspace which comes this bike vector, and with the orthogonal an orthogonal basis for the plane which is orthogonal to this plane, a basis which is orthogonal to this plane. So these angles are related with the Jordan angles with the formula, with these formulas. So with this result, we have thinking, instead of thinking about we have given phi 1, phi 2, we can think that we have given theta and theta orthogonal. So now we consider a generic bike vector, and these coordinates are in the sphere and these coordinates are also in the sphere. So if we impose the condition that the product, here is wrong. Well, here because we had that new one was this sum and this was this subtraction, then here should be A1 plus B1 over 2, and he should be A1 minus B1 over 2. But the idea is that this constant and these coordinates are constant, which depend on the angles. So the other coordinates, we can say that it is in a circle, which is the result for the paper. And now we have that instead of six coordinates, we have only 4, and these are related, so we have only 2 degrees of liberty to choose these coordinates. So we ask ourselves, is it possible for an immersion to have by its associated bike vector for the tangent plane in the point UV this exactly bike vector, which we are taking one variable for this circle and another variable for this circle. What we are asking in a graphical way is that the bike vector goes around this circle and goes around this circle, and the height and the radius of these circles are determined by the Jordan angles that we have, that are given for us. So for this bike vector, now we want to go to the tangent plane to define the immersion. So for going to the tangent plane, let me change a little bit. Now we have u minus b and u plus b and a sinus minus here. This is only because the tangent vectors that we get are more easy to write. This is only because this. If we don't make a change here, we have here a u minus b, and here we have u minus plus b. So this will be our tangent vectors, and this is a circle in capital pi and a circle of radius 1 in the plane orthogonal to capital pi. So the first tangent vector is a linear combination of these circles, and the second is the combination of the derivative of these curves. So now we go to the parameterization. We want a parameterization with these vectors as the as the basis for the tangent plane, and this is 4 functions that will depend on the angles, but also have to verify the compatibility equation. And this gets us to a first order PDE system, like the existing result that I have comment. But we also get a second order PDE, and the order functions can be written in terms of a solution for the PDE. But this PDE now it has a method to obtain explicit solutions. So we can generate different solutions, and for this talk, let me use this one, which is an exponential, and this one, which is an hyperbolic sinus. So the buildings are built like you are thinking. We take the expression we have and we integrate. For the first one, we have this, which is exactly our family T that I have defined before. And for A2, we have another kind of immersion that do not belongs to the family T. So the result that I have talked about earlier, this is the property that characterizes this subfamily. So as I said, these solutions gave all the immersions in the family T, and all the family T's comes from a solution of this kind. So we want to show that if you get a constant Jordan angle surface, then belongs to this family if and only if this ratio is constant. We already know one implication, we now want the other implication. And don't pay too much attention to the word regular. This only means that we are not working with planes, because if we are working with a surface which is a plane, it is trivially a constant Jordan angle surface, but we cannot define this well. We have 0 over 0. So regular means that this is not a plane. And this is the result that we think that resembles to the Lancre theorem, because we have for one head this condition that looks like, and this other condition that have the constant Jordan angle surface, which is a property, a geometrical property. So the proof is only a sketch. It is that we take a parameterization for this given constant Jordan angle surface. So for this parameterization, we have, remember that B can be written in terms of A, but let me write B for now. Ooh. So for this parameterization, we compute the invariance. We get that the Gauss curvature and the normal curvature are vanishing, that it was known. We get the expression for the others invariants. Now we study the ratio that we know that is constant for the family T. So this ratio it can be written in this way. So this will be constant if you only if this function A over B and B over A is constant. So this is because B can be written in terms of A, of the solution A. This is a PDE of first order, but we also have the second order PDE that have to verify A. So the only solution for these two equations are these kind of solutions. A pair of notes for finishing my talk. Well, we know that we are, for the result, we are supposing that we have already an CIF immersion. We know that this is not the Lancre theorem, because Lancre theorem says that we have any curve, and if you have a condition for the invariance, then it is an helix, and we have this hypothesis that we want to remove, but for now we only have this result. This was the stick, now the carrot, which is that the family, this is actually a characterization, because this family T is not all the constant Jordan angle surfaces, because the second example that I have built, which were given with a solution that was an hyperbolic sinus, then if we compute the ratio, we get a non-constant function. So we know that this is a strictly subfamily of the constant Jordan angle surfaces, and we have a characterization for this family. And that was all. Thank you for your attention, y feliz cumpleaños, Federico.
Do you have any questions or comments? Pierre Rayard, you have some.
He already has asked me something.
Okay, so